Assalamualaikum warahmatullahi wabarakatuh and a very good day to Dr. Faisal. So my name is Abdullah Hanan bin Shamsuddin and we are from Group 4. We are going to present about our project we call Sentry Eye, which is our small fixed wing surveillance aircraft. So basically on our project, we focus on designing and developing an aircraft that is simple to manufacture as well as for surveillance purposes.
Greetings, Dr. Faisal. I'm Chai from Group 4, machine number 206634. I'll be presenting the market analysis of UAV system. Today, I will focus on the sector UAV for surveillance. This is the market size and growth of the UAV, which is you will encounter compound annual growth of 14% and market value will reach 53 billion by 2030. And the factors that drives the UAV market is the adoption of new technology, which is AI and sense and voice system. And second is military applications. Third is aerial photography, which is the GPS navigation. And there are drivers that drives the growth of the market, which is the Russian-Ukraine war, security surveillance, and emergence of commercial drones.
So this is for my part, which is the wing design. So I started the process of designing the wing by selecting the shape for our wing, and then after that, the airfoil selection, as well as we are going to cover the wing parameters. So based on the picture on the right side, as you can see from here, this is a rectangle wing. So we choose a rectangle wing or straight wing because due to the simple manufacturing and the simple design as well as the low that will result in a low construction cost. So this is suitable for low speed aircraft, especially for our civilian aircraft. And this kind of wing will have a better aspect ratio compared to swept wing. And if you can see on the illustration below, we incorporate the winglet because we would like to reduce the induced drag that is quite high in the rectangle wing. So for our airfoil selection, we have selected the NACA 65 4-421. This is mainly because of the superior lift to drag ratio of 152.17 that will serve as an advantage for increased efficiency for our project. And this will affect in the better performance in terms of range, endurance, and battery consumption. So the high lift to drag ratio also allows for better gliding performance, that it can maintain the altitude and cover longer distances with the reduced usage of the propeller. So other than that, the NACA 65-421 also have a docile stall quality, which is better than NACA 23024. So this will give a better stability for the aircraft, as well as will give a gentle and predictable characteristic during the stall, so that we can have a control and recover the aircraft better than NACA 23024. So this is the overall wing parameters that we have been decided for our wing, as well as we calculated. So the wing area that we designed is 0.15 meter cube, and the wingspan is 1 meter. The aspect ratio is 6.17, and we incorporate no high lift device because we decided that we want to have an ease manufacturing as well as easy control. So we don't incorporate high lift devices. And then we have the ideal lift coefficient of 0.3, maximum lift coefficient of 1.2995. And just stated before, the airfoil that we are going to use is this kind of airfoil, and the angle of attack is 2 degrees. And the maximum critical angle of attack before it enters the stall region is 10 degrees. So that's all for the wing design. Thank you.
Assalamualaikum. My name is Mariana Akila binti Abdullah. My matrix number is 206646. The fuselage is designed for surveillance purpose such that the camera, battery, motor, servo, control unit and wire can fit into it. So the table shows the width and length for each component that will be used in this project as a guideline in designing the fuselage. Maximum diameter of fuselage, which is 0.22 feet, is calculated after considering the width of the widest component, which is motor, and the worthiness of each side. And for the fuselage length, which is 1.38, is obtained by sum up the length of each component with the space between them. This fuselage length is including the nose, cabin, and rear length. And for slenderness ratio, which is the fuselage to maximum diameter ratio of the fuselage, is 6.36. It is good in reducing drag and improving aerodynamic efficiency, even though it is not in its optimum value of 16. And this figure shows the side view and the top view of the fuselage design. This is the overall position of each component in the fuselage. The camera is placed at nose section so that it can give clearer view, while battery is placed towards the CG to maintain stability during flight. And the speed controller ESC is placed at rear section, which is near motor and propeller, to allow for shorter motor wire connections to avoid the interference of electricity. And this figure shows the total view and dimensions of the fuselage in millimeter.
And I'll be presenting about my design part, which is the tail. First, we selected the inverted V-shaped tail because of the engine is the pusher type. Inverted V-shaped tail will decrease the drag coefficient and make, which is the shape is more efficiency. And this is the parameters that we calculated in our reports. The tail planform area is around 0.25 feet square, and the tail taper ratio is 1, which is same with the wing taper ratio. After we calculate this, we have to select the airfoil, which is NCAA 3006. The thickness is only 6%, which is 6% lesser than the thickness of wing thickness to chord ratio. And this is the parameter for the airfoil. Now, finally, we calculate the horizontal tail span, which is 1.07 feet, and the chord is same throughout the route to the tip, which is 0.24 feet. And finally, we calculated the static stability to ensure that the tail design is stable for the aircraft, which is we get a negative value. And this is the image of a tail design, which tail arm is 1.8 feet, and the tail chord is 0.24. This is the cartier shape of the tail design. And that's all for my presentation today. Thank you.
Hello, Assalamualaikum. My name is Samir Akmal Sabah, matric number 207152. I will be presenting about takeoff gross weight analysis and better weight estimation for our project. So in our small fixed wing aircraft, the component will be motor, propeller, servos, speed control ESC, camera, battery, and also the landing gear, which the total of the mass for the component only is about 0.518 pounds. So the material that we use for our initial plan is styrofoam and also carbon fiber, which the total of the mass that we use is around 1.86 pounds. So the total of the total takeoff gross weight for our small fixed wing aircraft will be around 2.278 pounds, and it is quite heavy to be done, and we have come up with a better weight estimation, which is changes in material to the prawn foam and also balsa wood. So the total weight, including the components and also the materials that we use, is around 1.13 pounds, and the weight reduction that we get is around 52.5%. So this is very good weight reduction, and it can make our small fixed wing aircraft perform more better than the initial plan.
So moving on to the thrust to weight ratio and wing loading analysis. So for thrust to weight ratio, we use formula of thrust over weight, and then we got value of 0.82. And then for wing loading for takeoff, we use formula of takeoff parameters times sigma times lift coefficient for takeoff times thrust to weight ratio, and then we got value of 23.13 pound per feet square. For wing loading for stall, we use formula of half rho v square for stall and lift coefficient for takeoff, and then we got the value of 4.3 pound per feet square. For wing loading cruise max range, we use formula of Q, dynamic pressure, set by wing area, E, drag coefficient over 3, and then we got value of 2.85 pound per feet square. For wing loading cruise max loiter, we use also formula Q, dynamic pressure, set by wing area, E, drag coefficient equals to 4.93 pound per feet square. And then for the wing loading in tensionless condition, we use formula dynamic pressure, lift coefficient max over n, and then we got value of 1.08 pound per feet square. Wing loading sustained turn, we use formula dynamic pressure over n set by area E, drag coefficient, and then we got a value of 1.323 pound per feet square. And then for wing loading landing, we use formula sigma, total landing distance, and lift coefficient for max over 80, and then we got value of 0.13 pound per feet square. So that's all for the analysis. Thank you.